Navy AD-2s were instrumented for blast and thermal radiation response and were flown at near critical distances from several bursts. Results indicated that comparatively moderate thermal inputs may seriously reduce the blast resistance of some aircraft components. Standard blue aircraft paint proved clearly inferior to white or unpainted metal surfaces for protection against destructive thermal effects. Similar flights by manned and instrumented Air Force B-50s and a B-36 gave structural response data needed to establish minimum safe operational parameters for high-performance bombers. Other bombers from the Strategic Air Command flew in with the drop plane, testing techniques for obtaining yield, height of burst, and ground zero location, the three essential parameters of IBDA, Indirect Bomb Damage Assessment. On the biomedical program, Air Force QF-80 drones, instrumented to measure gamma radiation and with test animals aboard, were flown through atomic clouds at 30,000 and 32,000 feet. They were each controlled by primary and secondary motherships, and manned fighter escorts stood by to shoot down any drone that malfunctioned. These tests indicated that personnel of pressurized aircraft passing at 400 knots through a cloud at least 4 minutes old from a weapon of less than 30 KT would receive an external dosage of less than 50 Roentgens, with a negligible respiratory hazard. On the thermal effects program, one project concerned parked aircraft and aircraft components, an extension of previous tests. New data were obtained on structural weakening from thermal inputs too low to cause visible damage. Cloth thermal shields were proved to have considerable value in reducing damage to parked aircraft. Some aircraft fabrics were destroyed at levels as low as 2 calories per square centimeter, while magnesium sheet and foil-covered panels were undamaged by 20 calories. It was also found that strong tie-downs may protect aircraft parked nose-on to the blast from much of the damage that will occur if the plane is unmoored and free to lift and roll. But for side-on or tail-on orientations, the tie-downs may actually increase damage. Another important section of the thermal program was a study dealing with normal city vulnerability to fire started by atomic weapons. 3 cubicle houses 7,700 feet from zero were erected for one phase of this study concerned with exterior kindling fuels. The first house has a clean, safe yard, but dry rot is working in the unpainted siding. No rot here, but toys, weeds, and trash against the fence. A clean yard, painted fence, and maintained siding. Number 9 goes off. 13 calories per square centimeter. Overpressure 3.5 pounds per square inch. Time sequence photography shows the results. Destruction on the right from the yard trash which set fire to the fence. On the left, rotted wood in the siding was the ignition point. Sound painted wood and a clean yard allow the center house to survive. The fire hazards in these projects are not unusual either. 6 big American cities were inspected to ensure that representative conditions were tested. Conditions which suggest that a bomb of even this nominal power could start more than 100,000 fires over 25 square miles of urban area. Our next thermal project, run on Shot 10, required a new instrument line east from ground zero, roughly opposite the main blast line, equipped with thermal recording devices and with blast gauges at 0 and 10-foot heights. The first phase, designed to find out how much protection white smoke would give against thermal flash, employed a standard oil fog over a portion of the new line. In theory, this smoke would scatter and reflect fireball heat. This was a small-scale experiment, but evaluations have indicated that attenuation of radiant energy approached 99%. To explain the second phase of the project, employing black smoke, we must go back to Tumbler Snapper. On the low-altitude burst of Tumbler 4, high-speed cameras recorded a phenomenon never noticed before, a shock wave preceding the main shock front. Here it is again. This precursor wave, as it was called, registers on blast line instruments with a pressure time graph of this type, showing a considerable climb and duration before arrival of the main shock front. A normal shock wave with no precursor is quite different, hitting the instruments with an instantaneous pressure jump. The mechanics of precursor development appear to be these. A weapon bursts, and thermal radiation creates an intensely hot ground layer of air, a layer filled with dust from what is called the popcorning of the hot ground. Milliseconds after the thermal flash, the incident shock wave reaches the ground and expands, trailed outward by the usual reflected wave. Then a new wave, the precursor, begins to build out from the base of the incident wave, racing ahead through the heated air layer. An intense dust cloud follows closely, rising initially to about 50 feet and later to several hundred feet. One important effect of the precursor is to lower peak static pressures without a corresponding reduction of dynamic or wind pressures. The precursor builds steadily in height, but does not seem to inhibit formation of a Mach stem, though exact dimensional relationships are uncertain. Eventually, running into cooler regions, the precursor slows and is overtaken by the Mach stem. From that point on, the blast wave structure is normal again. It should be emphasized that a precursor can form only if the ground air layer is sufficiently hot. So if height of burst is increased, yield must be increased. Without the yield increase, the ground air will be too cool for precursor formation, as was the case on Shot 9, our first effect shot, 26 kT at 2,400 feet. Shot 10, 15 kT at only 500 feet, developed a strong precursor. It was on this shot that we ran the smoke experiment. A carbon black smoke was established over nearly a mile of the new instrument line. We expected that the top of the black smoke would absorb thermal energy and produce an extra hot layer well above ground, possibly generating a controlled super precursor at that height, or in some other manner reducing blast effects on ground targets. The experiment was handicapped to an unknown degree by wind billowing the smoke up to 300 or 400 feet, modifying the planned geometry. As it happened, the ground-level precursor, which developed under the smoke, was stronger than the one in the clear, although it extended only half as far before decaying to a conventional blast form. This test was not conclusive as to the effects of a heat-absorbing black smoke on blast. A further precursor study was set up to determine whether ground surface heating from thermal flash could generate a shock wave before arrival of the normal shock front. Panels 10 feet square, faced with variously heat-absorptive and reactive materials, were tilted for maximum exposure to the thermal radiation of the two effect shots. Post-shot study of the gauge records showed no clear evidence of thermally induced shock waves. We come now to the biggest program, the primary reason for Shot 9, the first effect shot. The biggest program in sheer volume, in theoretical predictions confirmed or refuted, and in the mass of empirical knowledge gained. 28 separate projects came under this heading, beginning with basic measurements on simple cylinders and rectangular concrete slab structures in a number of orientations. These passive targets, heavily instrumented, were not designed for response by displacement, but only to record shielding and loading factors at various heights and aspects. The findings of this important job can now be extrapolated for prediction of blast loading on a great variety of targets without direct testing. We begin to bump into the precursor again. A truss bridge section 2,300 feet from zero. Shot 9, 26 kT, 2,400 feet high, produced a small permanent set in the top chord with an overpressure of 11.5 pounds per square inch. But the Mach stem had not formed to reach the height of the bridge. 8.5 pounds did this on Shot 10, 500 feet high, 15 kiloton yield, with a precursor blast wave and a Mach stem already higher than the bridge. Apparently, for wind or drag-sensitive targets of this type, a low burst is more damaging than a high burst at similar peak pressures. A test of Army prefab Bailey bridges. Shot 9, 4,100 feet from zero. Essentially undamaged, the bridge slid back on its piers as expected, moving 43 inches from a peak pressure of 8 pounds. 9 pounds from shot 10 hits another bridge. Movement out of all proportion to that caused by almost the same static pressure on the first shot. Army equipment, which included 54 trucks and jeeps, was exposed to shot 9 pressures ranging up to 21 pounds to the inch. Thermal input reached 130 calories per square centimeter. Damage was generally moderate, as expected. All but 2 vehicles, one with burned tires and one with a missile-punctured radiator, could be driven away under their own power. For shot 10, Army tanks, artillery, and 22 trucks were exposed to pressures expected to range from 3 to 55 psi. Once more, damage was much greater than expected. Equipment was not merely overturned, but often torn to pieces or hurled great distances, at overpressures from which no such effects were predicted. Pressures which had done negligible damage to identical items on shot 9. Obviously, shot 10 was handing out surprise data. It was evident that our old static pressure criteria were not valid for predicting damage to wind-sensitive targets in the precursor region of low bursts. Not only were there violent high-frequency pressure fluctuations in this region, but the precursor depressed static pressures no longer had the same relation to dynamic or blast wind pressures found in a normal shock wave. Standard command posts, foxholes, and machine gun positions were located on shot 9 at 600, 800, and 4,000 feet from zero. Overpressures 8 to 22 pounds to the inch. General analysis indicated that cover-supporting timbers began to fail at 8 psi, while revetment stood up to around 20 pounds. Conventional sandbags tended to catch fire and spill their contents. One interesting finding was that foxhole covers can greatly reduce inside pressures, which may otherwise build to twice the outside pressure. Field hospital installations were displayed for shot 9 at ranges around 4,400, 9,000, and 15,000 feet, in both above ground and dug-in positions at each location. Radiology sections, operating rooms, pharmacy tents,